Hello, welcome to this presentation. I will be presenting our paper titled TBD Pedestrian Data Collection towards Rich, Portable, and Large-Scale Natural Pedestrian Data. Prior datasets often have several limitations. Recent datasets all favor quantity, so they do not label pedestrians. Other datasets often only contain pixel-level information in the form of, for example, bounding boxes, or their labels are only produced by an automated pipeline, which may contain errors. Datasets who have good labels of pedestrians are often limited in scale. In our case, we try to move beyond these limitations while also can have a novel combination of three features. We have human verified labels grounded in metric space. We have a combination of top-down views and egocentric views. And we have naturalistic human behavior with the presence of a robot. First, it is very important to have human verified labels grounded in metric space for the dataset to be useful in a robot navigation case. Datasets such as the Stanford drone dataset only have the annotations in the form of 2D bounding boxes, so we do not know exactly where the pedestrians are with respect to the robot. Having these type of labels is also the reason why ETH and UTY datasets are the most popular datasets used by the research community in navigation settings. Secondly, our dataset has both top-down views and egocentric views, whereas prior datasets only have one of them. Top-down views alleviates the limitation imposed by pedestrian occlusions, especially in very dense environments. So leveraging this benefit, we annotate the pedestrians for the top-down view. However, in robot navigation, the robot often only relies on its egocentric onboard sensors. So it's also important for the dataset to have these sensors. In our dataset, we can see that we annotate the data from the top-down views as shown on the left, while also project the annotations onto the robot's egocentric perspective as shown on the right. Thirdly, we have natural human behavior with the presence of a robot. The robots used in prior egocentric data sets often use robots that are either tile-operated or following just fixed directories. This means that their navigation behavior often has certain artifacts and are not representative of how humans truly navigate. In our case, our robot is a suitcase robot. With a suitcase handle, the human operator drags the robot back and forth across the scene to collect data. This ensures that the robot's motion is very human-like. Furthermore, our robot is disguised as a suitcase. This reduces the curiosity effect from the nearby pedestrians. In terms of the overall setup, the blue circles indicate the locations of the static cameras. The white area is where we collect the data, and the green rectangle shows a person carrying our suitcase robot and collect the data. This is a video of our data set. As you can see, we collect data in this atrium area, and oftentimes the crowds can get really dense. However, even with heavy occlusions, the robot still knows exactly where the surrounding pedestrians are in the metric space. We use a semi-autonomous labeling to produce large quantities of data in a short time. We use a state-of-the-art tracking model to track the pedestrians from the top-down view. The tracking model can help us label about 95% of the pedestrians automatically. However, for the 5% of the pedestrians, it is a very cumbersome process to fix their labels. As a result, we developed this web-based application so that the users only need to watch videos of the tracked trajectories. When the users notice any errors, it only needs to tell the app what kind of error happened and where it happened. So with just 2 clicks, the error will be fixed automatically. With the help of this application, it only took one trained annotator about 30 hours to label 375,000 frames of data, which contains 10,300 trajectories. With the help of this process, our dataset is already the largest among all the other datasets who have human verified labels grounded in metric space. This is still an ongoing process as we are collecting more data in more diverse locations. So please stay tuned for more information. We perform some evaluation on the data we have collected so far. We evaluate our dataset on tracking duration, motion speed of the pedestrians, and minimum distance between pedestrians. This kind of represents the density of the scenes in the datasets. In terms of tracking duration, our dataset has the second highest tracking duration and the second highest diversity in the tracking duration. Other datasets have pretty equal diversity in terms of pedestrian motion speeds, but numerically, our dataset is the second highest among the bunch. In terms of density, we also have very great density with the second highest density, and we also have very decent variation. So I would say our dataset does pretty good in these metrics. Furthermore, we evaluated these trajectory prediction models that are highly fine-tuned on ETH and UC5 datasets on our dataset. Now, it is very trivial for these trajectory prediction models to predict the future of static pedestrians, and their prediction errors are often close to 0. As a result, when both static and dynamic pedestrians are considered, these models achieve better results on our datasets. This shows that our dataset has possibly a mixture of more static pedestrians than the ETH and UC5 datasets. However, when only dynamic pedestrians are considered, all the models perform slightly worse. This shows that there is a domain gap between our dataset and the ETH and UC5 datasets. That's it for my presentation. Thank you very much. And please follow this link to check out more about our dataset.